First, I'd like to thank the speaker for giving me the opportunity to report our talk on this subject, and also for urging me as the last speaker in the morning session so that I could catch up with my own talk. So this is a collaboration work with Takayuki and Liwei Lo and Professor Feng here, and this is our attempt to use the equation state to compare with this GW170817 event, neutron star. So the basic idea is that the equation state could determine the mass radius relation and also the tidal deformability of neutron stars and other compact stars. And those could also be found from astronomical observations like binary neutron star mergers or supernova collapse. On the other hand, we know there are information about this QCD vacuum and meson bosons, barons. And we are interested in that whether it is possible for us to find a top-down model to construct this equation state from a theoretical approach. So we turn to the help of this ADS-QCD correspondence and then find equation state from string theory as the SS model, and then use our equation state to check this tidal deformability and mass radius relation of neutron stars, and further compare with this neutron star mergers, and find that our result is in totally agreement with the experiment observation. So we are interested in this neutron star cases, and they are, by this picture you could say like most of the neutron stars, their masses are between 1 and 2 solar masses. And here is the event of these two neutron star mergers. We know that the mass in neutron stars. So there are already these models of matters in neutron stars, and in general, we are not so sure about the exact model. We only have many phenomenological parameters to add on, like this MIT back model and AGM model, etc. So, so what is the equation state? So the equation state of nuclear matter is the relation between this energy density and the pressure. So it has a parameter called the stiffness, which means like the energy density will rise when the pressure rises. So they will determine the compactness of the neutron stars. So in the observation, we found that if we want to have like more than 2 solar masses, we need to have stable equation states. So here is some examples of these equation states. And for example, if we have this MIT back model with this constant V, in this value, we found that it is difficult for the known model to have 2 solar masses. And so many of the possible approaches are like two thoughts. So what our theory is based on is like, first we use this holographic Yang-Mills theory and infuse this D4 branes with number of Alexei, and they play the roles like they host Yang-Mills and quarks on its world volume, and also this can they arrange space to host the gravity deal of this coupled world volume. So this strong weak duality is like the generalization of this ADS-CFT correspondence. We are considering actually two different geometries. One is called confined geometry, and the other is called deconfined geometry. So later we'll see like this geometry is more favored because it could restore this chiral symmetry. So in general, if we have this in this geometry, we will have this D8 and anti-D8 branes have to be connected. But in the deconfined geometry, we could have two possibilities. One is similar to this confined geometry, which you have in which you break the chiral symmetry, while the other configuration you will have the chiral symmetry restored. So the good thing of this model is that you could see whether the chiral symmetry is a break or not, from this picture. So we are considering this instanton profile, and here this rho is the instanton size, and we could restore this pot-like instanton case by setting this rho to 0. But you should be careful because you have to consider some of the dead functions. And then this non-billion DBI action is not so easy to deal with, but there are two ways, like whether you could expand that in up to quadratic orders of f of this non-abelian terms, or you can keep this non-abelian term to all orders, but keep them inside of this root. So when we do this numerical calculation, this approach is easier. So here is the phase diagram of this holographic QCD, and we mentioned before, like this only the deconfined case could restore chiral symmetry, and so we choose this model. And also this is for the case of the pot-like case, and this is the case for the instanton gas case, which you have a non-zero instanton size. But in the end, we actually choose this pot-like model because we are mainly interested in this area, which is similar to this instanton gas case, and it's easier to calculate. But anyway, the important thing is that when you have this instanton gas case, you could see the chiral symmetry is restored when you have enough higher enough chemical potential. And so the thermodynamics of our method is that this omega is this free energy density, and so this pressure could be the minus omega, and this baryon density and energy density could all be functions of them. And we have this boundary condition. This L is the distance between these two D8 branes. And the mu is this chemical potential, which equals to the value of A0 as the equation of infinity. So by this numerically solving those equations, we could find equation states from those equations. So in general, they will take a multi-polytropic form. So that means like a different polytropic form in different ranges of this P, QCD, and this energy density. So for example, if you want them to have this single polytropic form, then this Ki and gamma I are actually functions of the range of this PQCD. So the problem is that which range should we choose to extract the correct kappa and gamma? So it for example, like you see when this P is very small, you have a curve like this with this gamma is something approximately 1/2. But when you have P to a much larger range, it's something like a straight line, and with gamma it's something like almost 1. So the problem is to determine which range we should choose. And then it turns out that in order to have the neutron spiral state to in the core have the correct value, and also for the tidal deformation to have the sensible value, we need to change the range to start from 0 to 0.05. This is the range for the pressure. So in that case, we found this equilibrium state have a form of a double polytropic form with this like 4 parameters together with this kind of value. And you see, like in the beginning, it behaves like something like 1/2, and then it goes like a straight line. But this part, although it's very small, but it's very important to determine this neutron star configuration. So the other thing we need to do is like to change this QCD unit to the QV unit. Because we have different conventions. So after changing to QV equation, QV units, we found like there's actually only one parameter. We name it as A. So that's very different from the also known equation state from phenomenological studies, because they usually have a lot of parameters to determine from observations, but here we only have one parameter. So since now we already have these equilibrium states, we could put them inside of this QV equation. And this is a QV equation actually have three equations, but now we just need two of them to determine this relation between mass and radius, and also pressure and everything.
What's the meaning of this A?
The A is like actually we here from this QCD unit everything is determined, but when we change that to this TOV unit, there are something like you see like we need to actually this A is some combination of this parameter. So this K0, Q0 is something like fixed if we already fix this MKK. So in some sense, this is like A is the parameter of L to the -7 order. So and this L, as I mentioned before, this L is the distance between these two scaled L between these two groups. So this L is actually the only parameter we have. So this TOV equation, you see like we could determine this M and P as function of R as long as we know the equilibrium state, which means like epsilon is function of P. So you could solve this equation easily. And then there are also standard approaches to find these tidal deformations as long as you have this function, the relation between epsilon and P. And so in that case, you could calculate this log number K2 by this way, also by numerical calculation. So this is one of the examples, like a typical star when we saw using our equation states. So here you find a star with a radius of 12 kilometers, and this is the mass of it. You see it has this typical 1.4 solar mass masses, and this is a picture of this central pressure. The pressure falls down until 0 when it when the radius becomes larger. So actually, this is how we determine the radius of this neutron star, because like in general, we would like to say like if you are exactly outside of a star, then your pressure will fall to 0. So that's how we determine the radius. So now it's time to compare our results with the observation. So up to now, there's only one gravitational wave observation of neutron star mergers but they have already offered enough useful information. For example, we know they have a total mass of 2.73, and one is like they are all around the mass of 1.36 solar masses. So also we have the other information, like they have this tidal deformability around this from like something like 70 to 720. So we need to make sure that our prediction, the prediction from our current state could satisfy this tidal information and this mass range at the same time. So yes, this is also from a LIGO Vocals paper. You see this is the relation between this two neutron star masses. So you could say this is almost a straight line, which means that the sum of the masses are something like constant, like 2.7. And here is like all this this tidal deformability of both neutron stars. So actually, they need to be within this range to be to make sure like the theory is consistent with the observation. So here you could see like most of these known equation states are already ruled out by this observation, because your top tidal deformability need to be around something like 500. So most of the known things are ruled out. So now let's see like our result. So as we mentioned before, we only have one parameter called A, which is proportional to L to the -7 order. So we say like we could have this possible range from 13,000 to 19,000, which means like we could easily find this obtain the two solar masses if this if L -7 is small enough. Also we could have this this pressure and mass pictures. So what people are interested in are this like tidal deformability. As we mentioned before, the tidal deformability needs to be around 500. So we have a larger picture, a more detailed picture of this one, which looks like this. Here we have to be careful that what LIGO measured is like the relation between is a lambda tidal, which means like some average between this lambda 1 and lambda 2. So in our case, this 6 means like 16,000 for the value of L to the -7, and then we say like in our study, like those 4 lines are they will satisfy this this tidal deformability constraint. But one needs to be careful that when this L to the -7 within these values, their masses are not so large. So you see, like they are actually just four lines, which has something like as high as like 1.6 or 7 solar masses. So that's our the weak point of our current study. So that means like if we need to satisfy this tidal deformability, we need to sacrifice our highest masses that we cannot reach these two solar masses at the same time when we satisfy this tidal deformation. But actually, for the study like Professor Lajima, like they have this statistics of all these known neutron stars. Like our case, we have this largest masses around 1.7 solar masses, and then in their study they show that there are actually 2 peaks of this neutron star masses distribution. So that means like one of the peak is like around this 1.7, and then there's some gap between 1.7 and 2. So which means that some possibility that for neutron stars more than with the masses between 1.7 and higher, there might be not pure neutron stars, but something like hybrid stars with some more dense cores inside, like a core star. So that's what we are going to do for the next stage. And also, one thing we need to comment is that the capital quantity state is about five times the nucleated state, which is according, which is good thing according to the literature. And the other thing, we are using this SS model, which is the G4D experience model. And before our study, there are some other studies using the E3B7 model. But in that case, we could not break this subspeed barrier. So, but in our case, you see except for the beginning area, it's very easy for us to break some of the barrier and with the causalities. So yeah, here's a summary of our study. So we have this equilibrium state in the compact stars, which could satisfy these observations in every parameter. And also, we are using a top-down model and only have one parameter. This is a great advantage to all the phenomenological models with a lot of parameters. So, however, we cannot have the two-solar mass configuration inconsistent with this tidal deformability at the same time. So we are trying to use this hybrid constant star core and the barrel shell. So the other possibility is so for simplicity, we only use the point-like case. So next time, we might also try this external product to find this whether the situation could be better. So thank you.
I just want to understand the status of this phase diagram. So, and compare with observation. So I mean, how is it? So the motivation for using a string theory model, is it because the QCD, well, basically people have the study of a color flavor locking phases and the color superconductivity has been going on for a long time. And if I last 15 years ago, there was another big development. So any of those simulation people did before and thinking about what the interior neutron star has actually been compared with the recent data or not yet? I mean, that's the first question. And second is that, do they match, do they not match, or are they all going to the same ballpark due to the fact that we only have one data point right now? Well, I mean, one or two, very few data points. At least you are comparing to one data point, right? There are now more neutron stars have been discovered for the experiment. And so do they match or do they not? And if they not, is the string theory really offering some help on this? Yeah.
Now we only have one data, but actually before that we already have something to judge whether equilibrium state is possible or not. First, you see here, one thing is we need to have we want to have two solar masses. So the old models, in the beginning, many of them cannot satisfy the two solar mass constraint, which you see here, this B is something bigger than this. So B is something like 218, and this thing is smaller than 1.78. So this is smaller than 2 solar mass. So this is one constraint they cannot satisfy. The other constraint is that we need to break this sound barrier. So that means only equilibrium states in this area are okay. So many of those models before, in the beginning they know themselves that they could not break the sound barrier. And also the other thing, also we only have one data now, but as I said before, even their conditions are very strict because they have both this tidal deformability and this mass range requirement. And actually the tidal deformability is very small. So you see here are also known phenomenological models before. So only this part are allowed by this experiment. So that means although we only have one data here, but already a lot of the known Zamolodchikov models are ruled out already.
So those are, just make understand, those are rolled out already by the gravitational wave data.
Yeah.
Oh, I see.
Actually, this is not the case because that means it's not ruled out. It's this equation. I think this problem is they problem the 90% confidence level and the 15% confidence level. So that means that 90% confidence level is very loose. So only the part. So some of the equations say when you look into the 50% confidence level is okay. So this equation say the choose okay to fit this data.
Yeah, but this part
these are 90% confidence level. It's not ruled out. It means that it's a more in a more large range. It's consistent with the large range.
When you write down the equation of state, how do you justify it? I think I asked, but when you can go back to the equation of state, you're adding the equation of state of two range.
Yeah.
How do you justify it?
Cause like this when we change this one thing is like when we change this this pressure is in terms of QCD unit. When we change back this to this DOE unit, it should like by this relation, like this P should when we change back this P back to this TOA relation, it should be around the range like 10 to the minus 4 to 10 to minus 2. So when actually when it takes the largest value in the TOA unit to 10 to the minus 2, you will here you will have like 0.05. So this is one thing.
But your kappa 1 and kappa 2 are not step functions. So you're actually adding two functions which shouldn't overlap, but they overlap.
It's like in the beginning we write it in a form like this with all four parameters not determined. Then you could fix this line and got all this number.
But isn't that from QCD you expect epsilon QCD equal to one constant like kappa times P QCD to the gamma? So you have sum of kappa P gamma I. I'm just worried about adding these two together, which shouldn't work with the same.
I mean, like when you fix this range, you have this result, and like it's not necessary to only have one single paratropic. This is something like Taylor expansion. So if you only have one single paratropic, it means like it's the first order expansion. But you expand it to high order, you could have like double paratropic or triple paratropic.
What is this? This expansion seems a bit arbitrary because your parameters are not like that. It's not like there's no suppression. There's no suppression.
This is not the expansion. This is the fitting. You fix some enzymes. You make a solve the equation, so you don't have the analytic form.
I know this is like from fitting, but how do you justify adding two?
Justification is very easy because if you using single paratropic to solve the TOV equation, if this gamma is equal to 1 or approximately equal to 1, the first thing we fit, of course, we only fit single paratropic, and then we realize if we solve the TOV equation, we cannot get the radius fixed because it's will be exponentially decay. So you never know where the radius. And then we realize this may not be the right way. So we just add another piece. And once we add this 0.5 something, then the decay is important because it will cut off the radius. Okay. So phenomenologically, if we only have one single paratropic, usually before we didn't solve TOV, so we don't know. But when we do the TOV solver, then we realize the other thing is important to cut off the behavior. So you basically have one behavior near the core, another behavior near the boundary. So you only have one polytropic. Usually it's very difficult to go to the, you can fit the core, but you can not cut off at the radius.
But then isn't that you should have two separate equation states because your core probably have different equation states?
Oh, that's because usually the real neutron star, you have several shares. But most mass, people believe most mass concentrate on the core, which are neutron core. On the outside, you have probably not a neutron anymore. So if we just, if the more resist model, you need to add something else. But that part will not be significant relevant in the mass information. So we just.
So it's like an effective equation state taking account of two different materials.
No, only one material, but still it's two. You don't necessarily to be polytropic. They are more single polytropic. You have more complicated equation state. For example, you just show this MIT back model. It doesn't look like any polytropic. Yeah. So it's not necessary to have only single polytropic. Single polytropic is the most easier one you can fit. But most of the model, of course, more complicated than this. If they want to fit the data, they usually it's very complicated with many parameters. So this equation they have the advantage of only one parameter.
We have a group